this video, it's the day after Thanksgiving. Why? You know what that means. No, it isn't. Please don't. No. Don't do it, no. Please. God, stop it. Stop embarrassing yourself. You gotta do this? What are you doing? No! It's Christmas! Spread to me.
In this video, I will be proving the first part of what's necessary for the analytic continuation of the zeta function and its functional equation. Now, the function I'm going to be dealing with this video, which will be used to prove the zeta function continuation, is the xi function, xi of z. Now, it's going to be defined as 1/2 z times z minus 1 times pi to the negative z over 2 times gamma of 1/2 z times zeta of z. And this is, of course, for real part of z bigger than 1. So that's just so that the Riemann Zeta function works in the ways we want it to work. And so this is only defined for real part of z bigger than 1 right now. But now you might wonder, why would we want to actually use this function? Well, it's actually because of the theorem I'm going to be proving today, which is that it can be extended or analytically continued to the entirety of the complex numbers. Every single complex number will have a value for xi in the analytic continuation, but it also has the property that xi of z is equal to xi of 1 minus z. And now this is one of the most important properties of this function, which is why we're using it, and it's why it's so stupidly complicated like that. And we'll actually use this fact right here to prove the functional equation for the Riemann Zeta function and the analytic continuation, so that it's analytically continued to see, well, because the zeta function is literally right there, easily we can analytically continue the zeta function. And so that's the importance of this xi function. Now let's go ahead and prove the analytic continuation. Now I'm just going to recall the definition of the gamma function just to get this right here. So gamma of 1/2 z is just going to be the integral from 0 to infinity of e to the negative t times t to the 1/2 z minus 1 dt. Right there is the input, e to the negative t, t to the input minus 1. That's the gamma function. Now, we are going to do a substitution, which may seem kind of weird at the moment, but you'll see why we do it right after we do it. And it's going to be pi n squared u, which would mean that dt, is going to be pi n squared du. That's that simple. It's a very simple substitution, which gives us that we have the integral. Well, this is just order preserving, so we don't have to worry about it. From 0 to infinity of e to the negative pi n squared u. Multiply that by t, which is pi n squared u, to the power of 1/2 z minus 1. And then we multiply that by pi n squared du. Now this right here, I can simplify it quite a bit. I get the integral from 0 to infinity of e to the negative pi n squared u. Right there is just going to be pi n squared to the 1/2 z minus 1. I'm going to move that u away, and now I'm going to multiply this by pi n squared, which actually, if you look at that minus 1 and this right here, those cancel out because that's how exponents work. And now we multiply this by u to the 1/2 z minus 1 du. Now this right here is just a constant, and so we'll move that out. And what we'll actually do is actually move it to the other side. And so we get it that if we do 1 over that, I get pi to the negative 1/2 z. Oh, look at that. Times gamma of 1/2 z times n to the negative z. Now what I just did was divide both sides by this, and that 2 and the 1/2 canceled each other out. Now this is going to be equal to the integral from 0 to infinity of e to the negative pi n squared u to the 1/2 z minus 1 du. Now we have this n to the negative z. Does that not sort of remind you of zeta of z? Well, how about we sum over all the n's? So if we do the sum from n equals 1 to infinity, this right here just becomes zeta of z. So we have pi to the negative 1/2 z, gamma of 1/2 z. Sum over all those n's, you get zeta of z is going to have to be equal to the sum from n equals 1 to infinity, because that's the summation we did, of the integral from 0 to infinity of e to the negative pi n squared u to the 1/2 z minus 1 du. Now the thing about this right here is that I'll just switch the summation in the integral. Now the reason why is because of a special case of the Fubini-Tonelli theorem, which basically says, what the theorem says is that if I put absolute value signs there and there, so that the thing inside of the integral is in absolute value signs, and this converges, then it will work. Well, the thing is that on 0 to infinity, this is always positive, so I could just simply get rid of those absolute value signs. And now, why does this converge? It's right there. This converges, and so this must also converge. And remember, it's for a real part of z bigger than 1, so just wanted to make that clear. So now, what we can do is we can swap them. That's what the theorem says. As long as that converged, we can swap them. Implies we have the integral from 0 to infinity of the sum from n equals 1 to infinity. Now the only one with n actually in it is e to the negative pi n squared u, and we'll multiply that by u to the 1/2 z minus 1 du. What we're going to do is work with that summation right there, and I'll call this summation, well, let's just call it omega of u, because remember, u is the variable that's changing here. So omega of u, what are some properties of omega of u? Well, there's actually an even more interesting function, which is called theta. Now theta of z is going to be the sum from n equals negative infinity to infinity of e to the, guess what, negative pi n squared z. Now this function has a property, which I'm going to prove in just a second, which is that theta of z to the negative 1 equals the square root of z times theta of z. And this is for a real part of z bigger than 1. Now the way I'm going to prove this is by first just plugging it in. So theta of z to the negative 1 is the sum from n equals negative infinity to infinity of e to the negative pi n squared z to the negative 1. And then on the contents within the summation, I'm going to do a Fourier expansion, which, if you don't know how to do a Fourier expansion, I'm pretty sure I have a video on it. What I'm going to do is the integral from negative infinity to infinity, and I do this of e to negative pi. Now I'm actually going to have to change n to the variable we're integrating over, which I'll call t squared, z to the negative 1, times e to the negative 2 pi I n t dt. Now that's just the basic Fourier expansion. Now what I'm going to do is a u substitution, where t is equal to the square root of z times u, which also means that dt is the square root of z du. Because remember, we're not integrating over z. Z is just a constant. And so, or at least for now. And then we're going to have n equals negative infinity to infinity, summing integral from negative infinity to infinity of, well, because the square root of z du is right there, I'm just going to put the square root of z outside. And then I'm going to have e to the negative pi. Now t squared is of course going to be z times u squared. So I'm going to have z times u squared times z to the negative 1. Notice the z and the z to the negative 1 become 1 together. They cancel each other out. And so I can combine these into e to the negative pi u squared. And then this one, keep it in right here, minus 2 pi I n square root of z times u. And this is du. Now what I can do from here is create an even simpler expression where we have the integral from negative infinity to infinity of e, bear with me here, it's going to be negative pi times u plus in square root of z squared. Now, why would I do this? Well, this would give me u squared plus 2in square root of z, and then plus, or actually it's going to be negative n squared z. And then, of course, we have the negative pi, which flips all the signs, and plus that. And so right here is literally what we had right there. This right here is the thing we have to remove now. So it's minus n squared z pi, and then du. So we've just simplified this immensely, and then this combines to become the sum from n equals infinity to infinity of the square root of z. This right here, this part, has no u in it, so I can just pull it out. E to the negative n squared z pi. Integral from negative infinity to infinity, e to the negative pi, u plus I n square root of z squared du. This right here looks surprisingly similar to the Gaussian integral. What I'm going to do is I'm going to say v is going to be equal to this entire thing within that square. If I do that, I get the integral from negative infinity to infinity of e to the negative pi, all that stuff squared. And I actually don't need to change the differential because this is just a u plus some constant. So now I have this, which if I want to move that pi inside the square, I do a square root of pi. Then I can use a t substitution. I'm just using as many letters as possible, where this is going to be the square root of pi v, which would mean that dt would then be, well, it's square root of pi dv, and so we'd get the integral from negative infinity to infinity. We'd have 1 over the square root of pi outside, and then we'd have e to the negative t squared dt inside. Well, what is this? This right here is just the Gaussian integral, which I'll link a video in the description, is equal to the square root of pi. 1 over square root of pi, cancel each other out. We just get 1. So this integral right here, I just did a series of substitutions, is going to be 1. And so actually, I didn't even need to include all of this in the end, because it all just went down to 1. And now the square root of z can be moved outside the summation because there's no n in it. And I get the sum from n equals negative infinity to infinity of e to the negative n squared z pi. Or, in other words, that is the square root of z theta of z. Now, if you weren't exactly following this entire process, basically, I can prove that theta of z inverse is just square root of z times theta of z by using a Fourier expansion and the Gaussian integral, which is, pretty cool. And so now I'm going to erase this proof if you don't mind. Some of you may mind, but get off of my channel if you mind. This is the fact I'm going to be using. That was the proof. Okay, well, this summation, remember what we're using here is omega of u, which is from 1 to infinity. Theta is from negative infinity to infinity. And so theta of z, you can rewrite this as the sum from n equals 1 to infinity of e to the pi n squared z plus the sum from negative infinity to negative 1 of e to the negative pi n squared z plus 1. Because remember, if I plug in n equals 0 here, the entire thing becomes 0 at the top. E to the 0 is 1. Now I can actually flip these to be 1 to infinity again, because the fact I have n squared, and that's it. So it's symmetric. And so if I just flip it around the origin, it'll preserve itself. And so this right here becomes 2 times this sum, which is, remember, omega of, well, we're using z here, plus 1. So what I'll be doing then is omega of z to the negative 1. Let's look at what this is. Well, this is going to be equal to 1/2 theta of z to the negative 1 minus 1. That's just simple algebra there. Which is then going to be equal to 1/2. Right there, by this fact, is the square root of z times theta of z. And then minus 1. Which I can just distribute this to become 1/2 square root of z times theta of z minus 1. Now remember, theta of z is simply by this fact is going to be 2 omega of z plus 1, then that's 1 over 2, which gives us the square root of z times omega of z plus 1/2 square root of z minus 1/2. Alright, well, this is kind of strange. Why would we want to do this? This just seems to make it much more complicated. Well, when you see what we actually do, you'll understand it. Now I'm going to erase the board, except for the part where we actually have the integral. And this fact, just so you remember it. Let me just copy down this fact. So this is what we had this equal to. Now what I'm going to do with this integral is I'm going to split it up into the integral from 1 to infinity of omega of u, u to the 1/2 z minus 1 du, and the integral from 0 to 1 of omega of u, u to the 1/2 z to the negative 1 du. Now the thing I'm going to do with this one is I'm going to use the substitution v equals u to the negative 1. That dv is negative u to the negative 2 du, which would get us that this right here is equal to the integral from 1 to infinity of omega of u times u to the 1/2 z minus 1 du plus, okay, what are our bounds going to be? 1 over 0 is infinity. 1 over 1 is 1. Well, that right there I can turn into a minus, so I can flip the signs, and then inside of it I'll actually have negative u to the negative 2 which makes that a plus. So I have u to the negative 2 times, well, that's going to be omega of v to the negative 1 times v to the negative 1 half z plus 1 dv. What I did right there is use the substitution u equals v to the negative 1. Sorry, this should be v there. That should be a v there. Now the reason why it's a v there is because u to the negative 2 is v squared, and so I get 1 over v squared dv equals negative du, or negative 1 over v squared dv equals du. That's what I use there. This right here, omega of v to the negative 1, I can use this identity. Very nice. And so I get the integral from 1 to infinity of omega of u to the 1 half z minus 1 du plus the integral from 1 to infinity of, well, I can combine these two integrals to become v to the negative 1 half z minus 1, that's just because I added the exponents together, and multiply this by this thing, the square root of v omega of v plus 1 half square root of v minus a half dv. Now I can move this inside. I can move it into there. And then I get the integral from 1 to infinity of omega of u times u to the 1 half z minus 1 du plus integral from 1 to infinity of, I move that inside. What do I get? Well, right there I get a plus a half. So I get v to the negative 1 half z minus a half. And then multiply that by omega of v. I'm going to erase this fact now, if you don't mind. And then plus 1 half. Well, right there I also get a half, so it's v to the negative 1 half z minus a half again. And then minus a half. This is just the thing normally. V to the negative 1 half z minus 1. This entire thing. dv. Now this right here, because the bounds are the same, I'm going to combine it with that right there and factor out the omega of u, because they share the omega of u. So this is the integral from 1 to infinity, omega of u times, right there it's u to the 1 half z minus 1. Right here, it's going to be plus u to the negative 1 half z minus a half du. And then plus, right there, pretty obviously, I can pull out a 1 half integral from 1 to infinity of, now I'm going to replace the variable with u. They're just the same variable. They mean the same thing. I'm just saying u. I'm going to have u to the negative 1 half z minus a half minus u to the negative 1 half z minus 1 dv. Notice the parallels. U to the negative 1 half z minus a half, right there. U to the negative 1 half z minus 1, right there. It's just their conjugates. So now I'm going to erase this fact. We're going to use these integrals. Actually, we're not going to use these integrals because this one simplifies. This one right here. And so this integral is very easy to evaluate, actually. We get 1 half times, well, we just use the power rule. It's going to be 1 over this thing plus 1, which is negative a half z plus a half. Multiply that by u to the negative 1 half z plus 1, and this is plus a half. Minus 1 over this thing plus 1, which is negative 1 over z, times u to the negative 1 over z. This is from 1 to infinity. Now, at infinity, this is obviously going to be 0. Why do I say obviously? It's because the real part of z is bigger than 1. That's what I've told you at the beginning. And so this, right here, is actually less than 0. infinity to a negative number goes to 0. Now this right here obviously is also going to be a negative number. Infinity to a negative number becomes 0. So that right there is 0. And then minus at 1, which is going to be 1 over negative a half z plus a half. And then minus 1 over negative a half z. And that's that. Now if I bring the 1/2 in, I get negative, because the 0 no longer matters. Then I have 1 over, that right there is negative z plus 1. This right here, well the plus, the minus actually becomes a plus now, is going to be 1 over z. Which is then going to transform into being 1 over z minus 1, because the negative went in, and minus 1 over z, which, as can easily be shown, is actually 1 over z times z minus 1. Whew! So, what was the point of all that? Well, it's because this right here, I just evaluated it, becomes 1 over z times z minus 1. So let's just get rid of all that and write in 1 over z times z minus 1. Woo! Alright. We're almost done. We're in the home stretch now. Now remember, xi of z is 1/2 z times z minus 1 times all that. So let's just get rid of all the stuff in the middle and let's write out what we have right now. What do we have right now? We have 1 over z times z minus 1 times the, not times, plus the integral from 1 to infinity of omega of some value u times u is 0 to 2 plus u to the negative z over 2 minus half. Now, I want you to notice that everything on this side is just missing 1/2 z times z minus 1. So let's just multiply both sides by 1/2 z times z minus 1. Let's draw our big line out. Boop. Now this right here, obviously, is just going to be xi of z. Now this right here, this times that, right there is the denominator there, and so that just becomes 1/2. Now plus, now that's just going to stay at 1/2 z times z minus 1. And then we're going to have the integral from 1 to infinity of omega of u times u to the z over 2 minus 1 plus u to negative z over 2 minus a half du. Notice now that everything here is going to make it analytic except for this right here. Now, I'm going to prove that this right here is analytic on C, because remember we only had it that the real part of Z was bigger than 1. That's the only thing that we know this is analytic for, but I will prove that it's analytic on all of C next time. It's too much for this video. This video is so long. But as you can see, the second part of it, which is that xi of 1 minus z is going to be equal to, well, 1/2 plus a half times right there is 1 minus z times, that's 1 minus z minus 1, which is negative z. That negative, I can just flip the signs on both of these, so it becomes z minus 1, and then flip the sign there, which is just the same thing right there. And then I have the integral from 1 to infinity of omega of u to the 1 minus z over 2 minus 1 plus u to the minus z over 2 minus a half du. Oh, sorry, that's a 1 minus z there. Well, this right here, that negative creates that z minus 1 there. and then z minus 1 minus 1 becomes z over 2 minus 1 there. Right here, the minus 1 goes up to become a minus 2 over 2. Then 1 minus 2 is negative 1. Negative 1 right there, which then becomes negative a half minus z over 2. Basically, what I'm showing here is that that xi of 1 minus z is just xi of z. Oh my god. Just acknowledge how long it took us to get to this point. How many loops we had to hop through. How many different functions, how many different ideas we had to introduce in order just to extend xi. But it's all worth it because now we can extend the zeta function. Woo! Oh, okay, that's it.